Moira will talk to us on the energetic flares but few CMEs, the role of helicity in the lowest mass stars. I'll give you a warning 3 minutes from the end.
That's great. Can you hear me okay, Sandra?
Yes.
Super, okay. So my talk is following on very nicely from some of the earlier talks we had today about CMEs and energetic particles. And I'm going to talk about the relationship between energetic flares and CMEs on low mass stars, and in particular, the role that the magnetic helicity might have to play in this. So I've started us off with this lovely image of a coronal mass ejection from the sun. You can see the image of the sun with the X-ray emission from the active regions. This is where we might imagine that flares will originate from. And you can see this very extended region of mass being ejected. So we have the great advantage in the case of the sun that we can actually see the star we're looking at. We can produce images like this. But as the previous speakers, particularly Donna and Amanda mentioned, one of the reasons we might be interested in coronal mass ejections is because they accelerate particles. And there we go. I had the horrors there, my screen was not going to advance. So if we look at the image on the left, you can see this little cartoon with the sun, and this large loop here is the coronal mass ejection being ejected. And what we observe in the sun is that many CMEs are extremely fast, they're super alphenic. And so ahead of themselves, they drive shocks, they drive mass ahead of themselves. But more importantly, I guess for this talk, they drive a shock. And shocks are wonderful places for accelerating particles. So if we look at the cartoon on the right from Reams in 2020, this is a view looking down on the solar rotation axis. We see the sun in the center. The CME is this rather gray banana here. And the black line is the shock that it's producing ahead of itself. So particles accelerated in this shock are one of the things that concern us when we think about exoplanetary atmospheres. As was explained beautifully before, these can be damaging for not only the atmospheres, but for any molecules that might be hiding underneath the atmosphere. Now, we know a great deal about coronal mass ejections on the sun. So here we have the sun through its magnetic cycle. And the image on the right-hand side here, the sun in X-rays, is just to illustrate the effect of the magnetic cycle. If you look at the lower of the two panels, you see the sunspot number varying. And so this is outlining the 11-year magnetic cycle of the sun. What is plotted above here is the rate of energetic proton arrival. And you see two different things in this plot. First thing you see is the low amplitude curve here. And these are the fast particles that are produced by the galactic cosmic rays. And you see this is beautifully in antiphase with the sunspot number, as we've known for some time. But what we also see are these, what you might think of as outliers, or you can think of it as an upper envelope here. And these are the particles that are produced in the sun's coronal mass ejections. And if you view this as an upper envelope and you look down to the sunspot number below, you can see that the fast particles that are produced by the coronal mass ejections are varying in phase with the solar cycle. And you can see that the amplitude of variation is also really pretty large. Now, there are many ways in which we can look at the relationship between coronal mass ejections and different aspects of the sun's magnetic field. This is a particularly recent paper from Michalek in 2020. And what you're looking at is a plot of, if you look in green, the green part of the plot is just the sunspot number. So that's outlining the sun's magnetic cycle. If you look in red, we have the number of CMEs. And in blue is the tilt of the heliospheric current sheet. And because I really hate acronyms, I've put a little cartoon on the side to illustrate what the heliospheric current sheet is. So it's also been described as a warped ballerina skirt that surrounds the sun, and it separates the outward flowing magnetic field from the inward flowing. So this plots and the excellent correlation you see between the tilt angle of the heliospheric current sheet and the number of CMEs was interpreted to suggest that CMEs are influenced by the large-scale field of the sun. Now, we can play this game in lots of different ways. If you like radio emission, as it's clear from this morning's talk, lots of people do, you can plot the monthly CME rate for the sun as a function of time. That's time on the lower axis. And you see the black curve is the radio flux. This is the 10.7 centimeter radio flux. And in blue is the CME, the monthly CME rate. And you see a beautiful correlation between the two. Honestly, this is my last plot showing CMEs correlated with various different things. On the bottom here is CME rate. That's in the dashed line here. And the solid line is once again the 10.7 centimeter radio flux. The panel in the middle is the CME rate and the monthly sunspot number. So again, you see the beautiful variation through the sun's magnetic cycle. But the top plot is the CME rate. Again, that's the dashed line. And the solid line is the global current helicity of the sun's magnetic field. Now, I can show this information in a slightly different way. I can show it as a plot. This axis is the global current helicity, and this is the monthly CME rate. And you see this very nice correlation between the two, albeit with quite a large scatter. So why should we expect, or why should we not be surprised that the rate at which the sun ejects CMEs is somehow related to the helicity of its magnetic field? Well, this goes back a very long time. I think the first time I heard this argument, it was from a talk by BCool, and I was a grad student. That tells you how long ago it was. And the idea goes back to thinking about the two different things that the sun's magnetic field does for the corona. One of the things it does is that the magnetic field provides energy for the corona. It heats the corona, as you can see in this image. Now, the sun can respond to this heating that's being dumped in its corona by radiating. So the sun can always get rid of this energy that's being released by radiating it away. But the magnetic field also provides helicity. And the only way that the sun or other stars can moderate the helicity in their coronae is by ejecting it. So the only way to get rid of the helicity is quite literally to throw it away in a coronal mass ejection. So the argument goes that if you didn't have coronal mass ejections, you could never reduce the amount of helicity in the corona, or at least you could never moderate it, and helicity would build up indefinitely in the corona. So we can understand coronal mass ejections as the response of the star to its need to get rid of helicity. Now, I started off this talk saying that I was going to talk about the relationship between flares and CMEs and helicity. So if we have this very straightforward picture for the sun, what is the problem? Well, the problem is that the sun is not the only star. And this is a rather busy plot, so I'll take it slowly. It's a plot of the kinetic energy in coronal mass ejections against the X-ray energy of the associated flare. And if we concentrate to begin with on these red triangles, and this goes back to a paper by Jeremy Drake and co-workers in 2013, you see that there's a very, very nice correlation between the energy in the CMEs that are ejected and the X-ray energy in the associated flare. In fact, the coronal mass ejections from the sun take away about 200 times the energy that we see in the associated flare. Now, what this original paper did was not only to show this nice correlation between the CME and the flare, but to extrapolate it up to the very much larger X-ray flare energies that we see for other stars. And that's why there's a big green question mark on this plot, because if you were to consider typical X-ray flare energies for stars, then if you follow this green line, the associated kinetic energy of CMEs would be enormous. I think it was something like 1/10 of the bolometric luminosity of the star. It was something totally unphysical. So this immediately tells us that the correlation that we see for the sun cannot hold for other stars, cannot hold for more active stars. And this led to some lovely modeling work, looking at whether it was possible to smother CMEs. The idea being that on very active stars, which have very high energy X-ray flares, the magnetic fields are so strong that the coronal mass ejections can't escape. They're literally confined by the magnetic field. Following on from this, of course, there was also a lot of effort to try to detect coronal mass ejections in other stars and to determine what sort of kinetic energies they might have had. And those are the square symbols that you see on the plot on the right. So these are various different stars. One of them, YZ-CMI, will be very familiar to quite a few of you. It's one of the ZDI stars. And it certainly seems, on the basis of admittedly only a few cases where this has been done, it certainly seems that stars do not produce CMEs that have an energy commensurate with their X-ray flare energy, if we were to assume that all stars behaved like the sun. So what has Helicity got to do with this particular plot? Now, I don't know about you, but I have always found Helicity to be a rather slippery subject. So I thought I would start at the very beginning. So one of the simplest and most powerful ways to think about Helicity is that it measures the linkage of two fields. So if you look at my little cartoon here, it's a very sophisticated cartoon. If we have this blue field line here and this red one, you can describe the helicity in two different ways. You can say it's the integral of A dot B over the volume, where B is just the curl of A. Or equivalently, you could say the helicity is the linked flux of these two fields. It's the flux of one that links through the other. And you can see I've even color-coded my equation here. Now that sounds very simple, but there is a problem, and the problem is one that's common to lots of areas of astrophysics, which is that we never see everything. We might only see the contents of this dotted circle here. This might be the only part of this volume that we can actually observe. So if we look on the right, I've extracted out of this cartoon what we might actually see. And we might see something that looks like this, a part of the blue field line and a part of the red field line. We don't know what these field lines are doing when we don't see them. It's a bit like your children. When you can't see them, you know that they're up to no good. These field lines could be doing something entirely different. They could look like this. If this were the case, then in fact there's no linkage of these field lines. They don't pass through each other. But we wouldn't know this if we only can view a limited part of the volume. So this has been an issue for many years in the subject of helicity. The usual way to get around this is to say we'll only measure relative helicities. So we'll measure a helicity relative to something else. And the something else is usually the corresponding potential field that has the same boundary flux as the field you're looking at. But there is a different way to get around this problem, and that is to be careful in your choice of coordinate system. So we can get around these issues of needing a gauge, needing another field to refer to, if we express our magnetic fields in what's known as the poloidal-toroidal decomposition. And I ask you to bear with me because I know that many of you have a particular hate of this coordinate system, but it's really useful when you think of it in a spherical system. Because in this case, the toroidal field lines that you can see drawn here lie on the surfaces of spheres. The poloidal field lines, which I've drawn here in red, pass through spherical surfaces. That means that if you view a spherical surface, such as the surface of a star, you can see all of the toroidal field. It lies completely on that surface. And not only that, the poloidal field lines pass through this surface. So you can immediately capture the entire amount of the poloidal field that is linking through the toroidal field. It's actually even slightly easier than that. Of course, on stars, we don't map magnetic fields over the whole volume. We only can map them at surfaces. So we calculate something called the helicity density. You can think of that as being the integrand of this definition of the helicity. But when we look at a stellar surface, we can map the toroidal field, and I've just drawn some funky toroidal field lines here. And we can map the poloidal field that passes through the stellar surface. In fact, we only need the radial component of the poloidal field because the other two components lie on a spherical surface. So for the ZDI experts in the audience, this means that we only need the alpha and gamma coefficients of the spherical harmonics. So what do we learn when we map helicity densities for other stars? Well, this plot here shows helicity density plotted against the square of the toroidal field strength. This is a proxy for the energy in the toroidal field. And you see three different types of symbols. The yellow symbols are the sun. There are many of them because we have many observations of the sun through its cycle. And the symbols with the black circle around them are just averages over time to give you an idea of the progression of the sun through its cycle. The circles and the diamonds are all individual stars. The faint symbols are where you have many observations of the same star, and the symbols with a black line around them are averages over all of those observations. The diamonds show stars of mass less than half a solar mass, and the circles masses greater than half a solar mass. And the blue color is another indicator of the mass of the star. You see there's this lovely straight line correlation between the two over 8 orders of magnitude. And this is consistent both with mean field dynamo simulations and also observations of solar active regions. In fact, here are some observations of solar active regions here. Each symbol is an individual active region. And in fact, this is a relative helicity that's plotted here against an energy, but the scaling is the same. But there is a slight wrinkle in this argument. I showed you a plot for stars of helicity density against the toroidal energy. But if I were to plot it against the poloidal energy, I'd see something rather different. And I've just put a little cartoon here to remind you the toroidal field would be the blue one, if you had a simple axis symmetric system, and the red field lines would be the poloidal field. We now see that there are two branches. The branch on the right is predominantly stars less than half a solar mass, and this branch on the left is primarily the more massive stars. So if we were to pick some particular helicity density, we would see that there can be two different types of star with the same helicity density. This star here, which is on the right-hand branch, has a higher poloidal energy than the star on the left-hand branch, but it has the same helicity. So all these stars, these very low mass stars, have plenty of energy. They lie to the right of the diagram, but only the same helicity as their higher mass counterparts. So why is this? Well, to understand why this is, I'm going to show you two separate examples. I've picked two particular stars to illustrate the point. We've got GJ49, thank you, which is the slightly more massive star, and GJ1245b. Now, just a reminder, what I'm going to show you is a map of the surface of the star with the toroidal field lines shown here in blue, and I'm going to show you in color the radial component of the poloidal field. So let's start with GJ49 first, the slightly more massive star. The color bar shows you the strength of the radial field. It's about plus and minus 30 Gauss. And you can see it's almost axisymmetric. The contours are the toroidal field lines. So dotted is one polarity and solid is another polarity. So if I pick this toroidal field line at the bottom, you can see that it encloses poloidal field that is all positive. So the toroidal loops are linked by poloidal field that's always or almost always of the same polarity. If I look at the slightly less massive star, GJ1245b, you see a very different distribution of magnetic field. Again, the colors are the poloidal field, and now you notice it's 10 times stronger, it's plus and minus 300 Gauss. But if we look at this loop of toroidal field here, you see that it encloses both positive and negative poloidal field. The two polarities essentially cancel out for the helicity. And so although the poloidal field is very strong, the net helicity over the surface is actually only the same as the previous star. So what do we conclude from this? Well, we conclude that these very low mass stars, less than half a solar mass, are inefficient at generating helicity on the largest scales. If we think of something which you can refer to as the mean twist, which is the ratio of the helicity density to the energy density, you can see it on this plot here. These stars, the very low mass stars, less than half a solar mass, produce relatively little helicity for the amount of energy that they have, whereas the higher mass stars, the circles in this plot, are capable of producing much more helicity density for the amount of energy density that they have. So here I've just highlighted the very lowest mass stars to make that point. So what was the bottom line? We understand from looking at the sun that coronal mass ejections, which are important for the energetic particles they produce, are linked to helicity in the sun. We also have found, by mapping helicity density across stellar surfaces, that the very lowest mass stars are inefficient at generating large-scale helicity density. They have plenty of magnetic energy, but for that amount of magnetic energy, they seem to have relatively little helicity. So perhaps this might help us to understand this strange puzzle for the most active stars. And we can see it again in this plot here. They produce lots of X-ray flux. There's plenty of magnetic energy to power their flares, but perhaps they actually eject relatively few CMEs. And that's me finished before Sandra switches me off. Thank you.
Thank you very much, Moira. Are there any questions?
I have one question, but I don't know where the raise hand button is.
Just go ahead, Eleni.
Hi, Moira. Very nice talk. I'm wondering here, when you say that the helicity density is larger for the lowest mass stars, and you compare it with the poloidal energy, have you looked into the axisymmetric energy? In fact, I'm wondering, is it because the two stars that you showed, they are also very different in axisymmetry in your examples?
Yes, what we tend to find, if I can just go back, is that the very lowest mass stars, such as the one that you see here, they tend to have toroidal fields that are quite non-axisymmetric. So the stars on the higher mass branch tend to have more axisymmetric toroidal fields, whereas the lower mass branch, not all of them, but they tend to have more non-axisymmetric toroidal fields. And that's why they tend to have relatively low helicities.
So is the axisymmetry in the toroidal component?
It's often in both, as you can see in this example here. But essentially what is important, if you think of the axis of symmetry for the poloidal and toroidal fields, if you think of those as two vectors, when they line up, you have lots of helicity, but if they're not aligned, as you can see in this example here, then the helicity is reduced. So it's actually the non-axis symmetry in both of them matters, but what is more surprising is that the low mass branch typically has these non-axis symmetric toroidal fields.
Okay, thanks.
And Simon?
Yeah. You said earlier in the talk that helicity is lost through CMEs. Does helicity get lost in other ways? I mean, when you have a CME, you have a big eruptive event, it carries away helicity. But does the magnetosphere sort of leak helicity over a small amount over a long time, or do you need a big rearrangement in the magnetic field to get that?
So you can redistribute helicity within the magnetosphere by reconnection events. So you can shift it from one place to another. You can redistribute it around. You can push it from large length scales to small length scales, or the other way around. But the only way to remove it is to physically eject the magnetic field. So dissipation alone, while it gets rid of energy, it doesn't get rid of helicity. So yes, you actually physically have to remove entire plasmoids from the magnetosphere in order to shed helicity.
Okay, so CMEs are the only way to get rid of that?
Yes.
Okay, thanks.
I have a question too, if I can.
Yes, go ahead.
So in that direction, how would you know if you're probing just the large scale helicity, how would you know that you transferred for small scales, for instance?
It is, I mean, this is something that is argued about a lot in the solar case, is how helicity is distributed among length scales. Certainly with the, if I can go back, I go back to this plot. So this is relative helicity against energy for individual active regions. And of course, these active regions span quite a range of length scales, but the important thing here is the slope of this curve. The relationship between the relative helicity and energy for these active regions is the same as I showed for other stars. If I were to look back here, these yellow circles here, these are the sun observed as if it were a star. So this is the helicity on the largest scales. But the slope of the curve is exactly the same when you look on individual active regions.
Okay. Okay, thanks.
Of course, we all know that magnetic fields are sneaky and they do things on small scales which you can't see, which is very reprehensible of them. But yes, I'm going to stop there.
Thanks.
Okay, thank you very much, Moira. And